Okay, so core. For that sake, for the sake of defining a core, we strengthen the definition of individual rationality to coalitional rationality, and that means it is for any coalition, in particular for the individuals, but for any coalition, we want what the coalition gets to be at least what the coalition could have got alone. And then the definition of the core is that given a transferable utility game, the core is a feasible pair profile that is coalitional rational. So instead of requiring a feasible pair profile which is individual rational, what we did in the definition of imputation, here we say it should be feasible pair and coalitional relation. We write it in the language of there is no coalition, which is a feasible pair vector, such that a feasible and no feasible pair vector for the coalition, y, which could be more than what we get. So nothing, there is no way to get more on your own. That's another way to say that. And it's quite reasonable because we want no group of players to have a motivation to debate. That's kind of the a parallel of strong Nash equilibria. Now, please notice, however, that we don't ask here whether this debating coalition is itself reasonable, is itself stable. And there are other solution concepts which require this debating coalition to be stable, thereby minimizing the number of possible deviations. We don't do that in core, but just notice it. It's important to notice the properties of what we define. And of course, core is strictly stronger in general, which is stronger than the imputations because we require we require coalitional rationality instead of individual rationality. So for the singletons, that's exactly the imputations. And another interesting observation is core as a set in Rn is closed. It's not a vector which is closed and convex. Now why? We like closed and convex sets in our cores, right? So why? Because well, by definition, it's a feasible pair profile, which is said that nothing can strictly improve. And it can be said also in this language, which is basically saying that it's a feasible pair profile and no coalition in this profile, for any coalition. Here it was that no coalition can be improved, and here it's for any coalition, the players get at least what they could have got alone. Now that's a set of inequalities, both feasibility inequality and that's a strictly and weak inequality. So the set which corresponds to each of those inequalities is is closed and convex. And as we know, the intersection of any number actually of closed and convex sets is closed and convex. So core is closed and convex. Now let's look at some examples of the games you've already seen and on some new games. Now, the generalized three-player, I'm by the way following quite closely the book by Osborne and Rubinstein, but I also give some examples from the lectures by Ron Holtzman in the Technion. And so most of the things you can see in Rubinstein's lectures, book. But anyway, you have everything you need in the lecture. So the generalized three-player majority game. By the way, there is a book by Osborne alone, and that book, I think, maybe actually it's a similar book to the one by Osborne and Rubinstein. You may take a look at the book. I don't remember much from the book, but I don't know tell exactly whether you should take a look, but I remember it's quite similar to the book by Osborne and Robinson. So if you just like that, you would like, why not? You can find some. There are some, I think, tutorials which are allowed to, or which are provided by the author. I think provided to everyone. I'm not sure. Anyway, if you have this, when you buy that book or something, it can be interesting. But I don't say you should. No. If you decide to buy a book, it definitely is better to buy Osborne and Robinson. So back to the game. The generalized three-player majority game, that's an example from this Rubinstein. So the original majority game which we saw was for any n, and then we saw that if you have the majority, then if you have a majority, you get 1, so you may kind of pull off to push some decision you would like to push, and otherwise 0. Now, for n equals to 3, we can also look at this majority game, but they generalize the example for only for n equals to 3. They say that, okay, if you are the grand coalition, you get 1, but if you are only the coalition of 2, so you are majority, but you're not unanimously, you're not everyone, you get some alpha. And alpha is a parameter which is between 0 and 1 included. So that in particular can be the original game if you take alpha to be 1, but it can be something else. And for this game, so for n equals to 3, and for this game, that's what the game that we are looking at now. That's the game we looked at the previous lesson. We also will still look at this game soon, but as is. But now we're looking what happens for n equals to 3, and for this generalization with alpha. The conditions for the core mean that okay, no player gets less than 0, so it's a subset of r plus the power of n. Now the total is 1, and the coalitional rationality of the coalitions of sides 2, the coalitional rationality for those coalitions means that the total that the players get for any s of size 2 is at least alpha. Now, they've simply rewritten the conditions for the core. Can we say something else? Can we say something concrete? So what we can say is, or what we ask, when is this set not end? Okay, so what we can immediately say is that for this set to be non-empty, we need the sum of any two xi and j to be at least alpha. So the other one, since the total sum is 1, the other one is at most 1 minus alpha. Now, yes. Now, the one that the other one be most 1 at a time. Now, since this can be done for any k, so the ijk can be chosen to be any indices as long as they are all different. It means that any xi, any xk has to be at most 1 minus alpha. And as I said, their sum has to be at least alpha. So by substituting, that means that 1 minus alpha plus 1 minus alpha has to be at least alpha. And only if alpha is at most 2/3. So it's a necessary condition for the core to be non-empty. Now, conversely, if alpha is at most 2/3, the core is indeed non-empty. For example, we can look at this vector, it's in the core. It's non-negative, the total is 1, and for the sets of 2, it's always 2/3 exactly. Excuse me, it's 2/3 at least alpha, because alpha is at most 2/3. So we have now shown that the core is non-empty if and only if alpha is at most 2/3. An interesting observation from the example is that in particular the core may have different coordinates. So despite the game is defined symmetrically, there is at least not said what I mean by symmetry here, but there is no difference in the definition for the different players. They all play the same role in the definition here. But For example, if alpha is 3/4, the following vector is in the core. So core is a set which is not necessarily made of only the vectors which have the same values, even if that the game is defined in a way which does not depend on the identity of the player. Okay, another example. Now, as I said, we started with the majority game, which we saw in the previous lesson. We constrain ourselves to 3 players, and then we generalize it. Now, what if we don't generalize it? What if we just look at any at the original game on 3 players? Then this is the function, and this can be said that it's the same what we had in the example, just the one we've just seen. Then alpha is 1, because the S of size 2 will be included here, and it should be 1. Now, alpha should be 1. And as we've seen, for alpha equals to 1, strictly larger than 2/3, the core will be empty. So we know that the core will be empty. Now we can also prove, it's also an example from Rubinstein, that even the majority game on any number of odd players, but without alpha, simply of course just like that, 1 and 0, it always has the core, it always has an empty core. The empty core. Why? Why is it always empty? Okay, let's just write the conditions and see that there is nothing which solves them. So that's kind of a typical thing when we do calculation of this score. So assume to control the carry sum from the core. Since there are at least 3 players, then a subset a pollution of size n-1 is at least is always the majority. And the value is there for 1, right? That's the game you're looking at. And the x, so the total value of those players in the core, has to be at least 1 by the group rationality. The x is in the core. Now, the total number of collisions which have size n-1, each collision can be seen simply as the complement. So how many complements are there? How many singletons are there? Of course, n. Now, therefore, if we go over all the solutions of size n-1 and sum the x's for each such collision, we sum the xi's of each collision. Since we know the xi, that the sum of xi's in such a collision is at least 1, as we've seen, and for we sum them for each such collision. Now it's going to be summing once for how many collisions. So we are counting basically the collisions of size exactly n-1, and we've just said that there are n. So it's going to be at least, no, we are not counting. This is going to be not counting because that's at least 1. It's going to be at least the number of collisions, at least n. Okay, now let's count this differently, as we usually do in combinatorics. Now this sum of all the collisions of size n-1, and for each collision we start a count of the xi's in this collision. In other words, for each collision we look at the xs. It's defined as the sum of size collision. So we can look at this sum, double sum, in the different order. We can just look at all the players, and instead of looking at all the coalitions and the players in the coalition, we just look at all the players, and for each player we sum xi's over all the coalitions of size n minus 1, which include the player. We reverse order, and since finite sum of non-negative numbers, it's enough to say that the order doesn't matter. It's finite sum anyway. So we have to reverse the order, and then what we have. So for each player, how many coalitions of size n minus 1 are that include this player? A coalition of size n minus 1 is a complement. So it's characterized by exactly the player it doesn't include. Now, coalitions of size n minus 1 which include a given player characterized, they don't include exactly one player, but they always include that player. So there are exactly n minus 1 such coalitions. And therefore, n minus 1 times xi. So we just get n minus 1 out of the sum, and the sum of all the xi's is exactly, of course, 1, because it's what's the name? It's called a feasible pair problem. What a name. A long name. So it's going to be n minus 1 times 1 and n minus 1. But we've just proven that this sum is at least n. And that's contradiction, which means that the assumption that there is something in the core is wrong. So the core is n. Good. So there is nothing which is stable. Now, no way to divide the paths in a stable way, in the sense that the core means. Now, another interesting game is treasure. So assume that there is it's also from Osborne and Rubinstein. Assume that there is a number of people who found unboundedly many more than there are people pieces of treasure. So they are identical, and any two people, any pair of people, any pair of people can carry one piece. All unique, identical. So if the number of people is even, the value of this coalition is exactly half. Otherwise, it's minus 1.5, because one person doesn't carry anything. Okay, so what is the core? Empty, non-empty, what is it anyway? So for the even case, that slide deals with the even case code. Assume any couple, the total is at least the value of the coalition is at least 1. Now, since the grand coalition can be divided in the even case to couples in many ways, then it's going the total x of n is going to be n over 2. And we conclude, since we can be presented as the sum of, so the history as the x of n can be presented as the sum of couples in any way we want, that any couple has exactly the total, the sum is exactly 1. Now, then if n is at least 4, then it's even in at least 4, we claim that each one has value of exactly half. Why? Because if you have someone who is less than half, then in each couple, if you have someone who's strictly if there is at least one who has some I, where I is at least that is strictly less than half, then in any other couple, and there is such because n is at least 4, take the one who is not more than half. There is such. Then you just get the pair. Their sum now will be less than 1. You can. This is true for any couple. Sum is 1. It's a contradiction. So it has to be that if n is at least 4, and we can always have such two couples, and if we change them and prove what I just said. For any I, xi has to be half. Exactly half. So this vector is the only possible vector of the core. It's also in the core. So the core is exactly this vector, this singleton. Now, if n, however, is equal to 2, so if they're exactly two pairs, then the only condition is simply that their sum is 1, and we can divide anyhow between those. Okay, so that's what we have. Now we go to the odd case. Now, what if one guy has always to remain idle? So what is the core here? Now, here it's going to be interesting. There is no stable way to divide things, unless, of course, n is 1. But let's just talk about no stable way. Or about what happens is that in the general case. Well, one second. Yeah. So if S is at least 3, it's 2k plus 1, some k which is this one, then for any couple we have this one as we said before, and however, since the total sum is the value of the Lagrange coalition, which is n minus 1 over 2, because it's odd, we can conclude that you can just take any for any two different eigen's I and j smaller than n, the sum is going to be exactly 1, and the n has to be 0. Now, since this can be done for any, this proving that someone is 0 can be done for any agent, for any n prime, not only for the actual n. We get that in a core, any element has to be 0. And of course, that contradicts the claim that for any couple of different agents, the sum has to be at least 1. So there is now nothing in the core. Now, that's unless there is only one agent here, because in the beginning we assumed that it's 2k plus 1 when k is at least 3. Let me fix that. K is at least 1. Now, if there is only one agent, that's quite a degenerate case, but still, then of course the only condition is that that's at least 0, and that's exactly 0 because that's the value of the coalition of one agent. So then the vector of 0 is exactly stable, which is quite reasonable because if there is only one agent, you can always give that vector, that agent, the value that that agent gets, that all this. That v of one agent is always the only element of the set. Okay, so the next example is, that's actually quite a cool example. Indivisible good market. So that's an example also from Osborne and Rubinstein. And please take a note how it's defined. So there is seller, each seller is in a market, and there are sellers and buyers. Each seller holds one unit and has a reservation price 0. So it sells for a price at least 0. Each buyer needs 1 unit and has the reservation price 1. At most 1. It will pay at most 1. Now it means that everyone can trade with everyone because of the reservation price. Nice. So the question is simply how many sellers and buyers do we have? So we model this as the following of course, it is transferable utility game. The players are buyers and sellers, and the value of a coalition is the minimum of the intersection of S, the buyers, and the sellers. So how many buyers are there, how many sellers, and the minimum is the value of a coalition. How many trades are we able to do? Now, what is the core? Now we are going now to prove that if the values, the size of buyers and the sellers are not the same without the generality, it's defined quite symmetric. The story is not symmetric, but the game is defined symmetrically, so it's without loss of generality. Let's assume the bias, there is strictly more bias than the rest. Then the core is exactly one vector. When all the buyers get 0 and all the sellers get 1. So the sellers get all the power. Now think of it. It means that you have at least one more of the other kind. The kind which is scarce gets all the power. This can, for example, of course, up to the axioms which we need to assume. But if you have a case to claim that those axioms hold, then, for example, when we have heterosexual marriage market, if one of the sexes is scarce, and it's enough, according to this model, that there is one person less of one of the sexes, so that the scarcity, the imbalance is minimum. There are million people of one sex and 1,000,001 of the other sex. Already, of course, like those are people who are available, and of course, in real life, it's not really the people are identical and all that. So that's not like something you can immediately claim is true for the marriage market. Simply nice thing which you can use a very, very basic model. And for a marriage market, you need something more, something related to preferences and all that, something stable matching and all that. But if the goods are identical, then we see that immediately all the power goes to those Pascals, even if there is only one less of those Pascals. I actually remember watching this talk about that in the Conduct of Marriage Market by Dan Ariely, and he's a behavioral economist, so he is more for the sociological side of the business. But I don't exactly remember what he spoke about. He did speak about this, that a little imbalance can cause a great deal of power imbalance. So a little size imbalance can cause a great deal of power imbalance, but I don't remember exactly what he spoke about. Anyway, back to our work. So if we are talking about, by the way, another example, if we indeed talking about goods which are scarce, so the buyers are scarce, then of course they have the ultimate power. What does it mean? It means that they basically can extort however they want, if we assume those axioms. Okay, so now let's get to our proof, because the explanation what it can mean it's still not math, so it's something which is not exact science. So let's get to math. So think of the implications and let's get. So first of all, we need to show one direction, that if something is in the core, that I know we need to show that this vector at x hat is in the core. So that's simple because its value, its total sum of the values is L, the sum of the scalars of kind of the scalars, and that also exactly the value of collision. So that is definitely that holds. And then we need to also show that for any collision, now the total sum is going to be exactly the number of L's, and that's at least the value of this collision, because the value is minimum between the number of L's and B's in this collision. So that's a vector in the core. Now the other direction is that we need to prove that if something is in the core, it has to be like what we said. It's by 0-fold bias and 1-fold scalar. Now, given anything in the something in the core, any vector in X in the core, let B be A, maybe there are several, but A by with the minimum XB, and let L be A scalar with the minimum XL. So then, since AX is in the core, the sum of XB and XL, in particular those, are going to give at least the value of the collision, which is 1. Therefore, the size of L is the value of the line collision, is because X is in the core, the total of the X of the collision. By the definition of B and L, it's at least B times XB and L times XL, because B and L have been chosen to be those who get minimum. Now B is simply B minus L plus L, the size of B is size of B minus size of L plus size of L. And then let's open the parentheses. It's going to be size B minus size of L times XB plus size of L times XB plus XL. Now XB plus XL, we've just shown at least 1. At least 1. So it's going to be at least this expression. Now, since L, if it needs to be at least the expression, and B is strictly larger than size of B is strictly larger than size of L, as we assume, we conclude that XB is 0, and therefore, since the sum of XB and XL is at least 1, XL is at least 1. So, we have just shown XL is at least 1, and that's the smallest of the L's. So every L is at least 1, and their sum is exactly the number of the scalars. So they have to be exactly 1, each one of them, and then of course nothing is left for the others, the bias. So that has to be, X has to be exactly this vector X has to be defined this. Okay. And then another example, that's the game we saw already, the gloves game. We called the game on triple S when player 1 is always needed, so that's the only actually, that's a better player, and the coalition is winning. It's a coalition which has player 1 and at least one of the others, and losing otherwise. So in this case, the set of imputations is sort of all those that the sum is the value of the grand coalition 1, and of course nobody gets less than alone, which means that nobody is negative. So these are all the non-negative vectors such that the sum is 1. So this this is the basically the simplex. It's simplex, and then we ask what is the core. We need to add the collisional rationality conditions. So this collisional rationality adds the following conditions: that x1x plus x2 and x1 plus x3 has to also be at least 1. Well, yes, x2 and s plus x3 has to be at least 0, and that does not add anything. So what we need actually, what we need to add is that, and the whole system now implies that the only solution you can check is simply algebra, school level of algebra, is 1, 0, 0. That's the only, so the core is a singleton, and again, as before, the whole power goes to the guy who is unique, the vector plane. So the vector plane does need the others, but not necessarily exactly one of the others. So there is only one vector plane, and he gets everything. So you may discuss whether it's a reasonable way to allocate nothing to the others, but that's what you allocate if you assume the axioms of the core. Now, yeah, we have proven that under those axioms, the vector plane has absolute power. And now let us derive a specific condition that characterizes when the core is not empty in general.